for emitter. Okay. Minus plus free BE here, and then a plus minus free BC. So BE over free T minus free BC over free T. That's IS over free to R, free BC over free T minus 1. And IS over beta F free T. Minus 1 minus IS free BE free T minus free BC free T, and IB, it's going to be IS over beta F free BE over T minus 1 plus IS over R, it's free BC over free T minus 1. And here the IS is going to be related to the Gumbel number P over dn dx. Okay? So if dn is constant, you can get out of this integral, and then we are going to get the gamma number there, the dopant concentration in the base. And that is easy to measure. Okay, that is a base transport model. And today we are going to talk about the charge storage, and charge control. Model. And we are going to talk about the charge storage. There are two kinds of charges possible in the bipolar transistors. One is injected minority carrier charge. Minority carrier charge. Okay, and the other thing we have to think is the space charge. Space charge. Injected minority carrier charge is going to give us the diffusion capacitance. we call diffusion capacitance. And the space charge will give you the junction capacitance. This capacitance, this is related to the delay of the device with the delay of response. It's related to the delay of the bipolar transistors. So it is very important to understand what kind of charges sitting in the bipolar device. Okay, and then the injected minority carrier charge means when you have emitter and base, and the equilibrium values is going to go N P naught and P N naught, something like that, right? And then this is the P plus, and then this is the base, the N, and this lightly doped region, of course, it is N naught and P N naught, something like that, okay? And then we have injected carriers with the applied the voltage, and then that the carrier current is going to be, we have all derived this in the diode, okay, and P naught e to the v over v t minus 1. It can be said something like that. And IP is going to be QA dP over LP P n naught e to the v over v t minus 1. Yeah. So, we are very heavily doped emitter and the lightly doped base. This is a typical number for this is Na is emitter 10 to the 19th, while the base may be 10 to the 17th. So 1/100th of them. And this means Pn naught is greater than MP naught. So I is almost the same to IP. Okay. And then the way to derive the capacitance here, the charges, we have to get the charges first. Stored minority carrier charge. Now, the stored, that is significant. Qn is Qa and P naught e to the v over minus n ln, okay? And the Qp, which is not that big, but you can have the number e to the v over vt minus 1 lp, something like this. Pn means Pn naught greater than Np naught. So Q, the charge is stored in this junction by the injection of the minority carriers, is almost the charges in the emitter, and find the characteristic time tower, and by definition, tau is going to be the charge. Tau is going to be charge divided by the current. Okay? So you can get that Q over I, and then you just literally input all those figures, and amazingly you end up with very simple equations. Vt minus 1 over Q A dP P n naught e to the v over Vt minus 1 equal to LP square over dP, and that is tau p dP over dP, and that is tau p. Okay, so this is the values. LP square over dP is going to be the characteristic time, which can be defined by this. Now, how this thing is going to be related to the junction capacitance? The capacitance is nothing but the dq over di, dv is the capacitance, and we know the q is going to be lp p n naught e to the v over vt minus 1, and so dq over dv, which is the capacitance, is going to be qa lp p n naught v over vt minus 1 over vt. Okay, and that is going to be charge the thermal voltage. This is the thermal voltage. Thermal voltage, which is kT over Q. All right. So Q is going to be I tau P dq over dv, junction capacitance is going to be tau p over I over Vt. Now, we have another charges, as I mentioned in the early of this lecture, that we are going to have another capacitance which is related to the space charge. And for that, we can set QVE and QVC. This is related to the emitter and base junctions, space charges, and this is base to collect the space charges. Okay, this characteristic, this junction capacitance that we have talked about is based on the fact that the charges, forward the charges is going to be tau f. We have characteristic time. We just define the characteristic time right here. And then QR is going to be emitter current and tau R. And this is VBE, forward bias, and VBC is reverse bias and or zero, or VBE is negatively charged. So we newly define these charges, not just the QF and QR, we're going to define QVE and QVC, which is related to the space charges. These are the charges related to the injected minority carriers. Okay? These are the charges, the new charges, which has to be in the space charge region. And we have two space charge regions, which is in between emitter and base and collector. Okay, how that is going to be related to the capacitance? In the space charge regions, we have XP and XN, okay? And then there's no free carriers in this space charge regions. Now this is P plus and N again, like as we discussed before, the diffusion capacitance. And since there's no free carriers in this space charge regions, we just have ionized dopants. And this ionized dopant is not moving. So it is, we have a localized charges or something like this. And here we have equilibrium values. For holes and electrons, and here the lightly doped base also we have equilibrium values like this. Right. The applied voltage VA will modulate the space charge length. This is a total, is the XD, right? Depending on the applied voltage, the XD is going to be changed. Okay, and then it just like the space, the capacitors with the different distances, variable distances. XD naught VA is equal to 0. Okay, XD VA, if the applied voltage is greater, big, then the space charge regions is going to be changed. VA is negative. This is how the space charge region length is going to be modulated with the applied voltages. In other words, if it is a forward biased, then the space charge region is going to be decreased. And then it's a reverse biased, then it's going to be increased. The space charge region is going to be increased. So obviously we can see that it is a capacitor with a different D's, and that is going to be changed with the applied voltages, VA. Then it's not that difficult to get the equations related with that. So now the junction capacitance dq over dv is going to be CJV. We call the junction capacitance, which is variable with the applied voltages. Then CJ0 means the junction capacitance at no applied voltages, and then it's going to be corrected with this equation. And for step junction means we just clear-cut junction, no graded regions of the dopants, the step junctions. The junction capacitance turned out to be ND, NA. This is what we have done for the diode, okay, analysis, DA and NA. So you can find the derivation of this in the literature. Okay, and then here the M is going to be 0.5, and the phi I is going to be thermal voltage again, ND NA over NI squared. We have covered this in the diode case. So without any voltages, just if you make a junctions, p-n junctions, then we do have a space charge region like this, which can be regarded as a capacitor, and then that the distance is going to be modulated with the applied voltages, out of circuit applied voltages. So without any voltages applied, then the junction capacitance can be totally determined by the dopant concentrations here. That is the only variables we have. Now, to find the charge added to each plate of junctions for a given voltages, we can see that the D or Q over D V, that is capacitance, and the dQ is C V dV, and the Q is integral V1, V2, Cj 1 minus V psi I minus mdV. And the Q is going to be Cj minus psi I 1 minus m 1 minus V over psi I 1 minus m V1 to V2. The charges which can be stored by changing the applied voltage V1 to V2. And so QVE, that is the charges which can be in the space charge region between emitter and base, right? And that is going to be BE over CJE over 1 minus V over psi I. This psi I is going to be base and emitter psi I. Okay? And that is M. M value is for the base and emitter, so I have to write down something like this. Okay? And then QVC is VC CJC here 1 minus is almost the same formula. Psi I now is BC and MBC dV. So this terms is depending on the applied voltages. The V, the junction capacitance is going to be changed with the applied voltages, and said the M is about the 0.5 in the step junctions, but usually it has to be determined empirically, and it's in between 0.3 and 0.5. The M has to be determined empirically depending on the device, because you cannot exactly control the slope of the dopant concentration in the junctions by any means in the real process. So we have seen that there is two capacitance possible. One is the injected minority carriers, and then one is the built-in space charge regions capacitance, right? And both of these two is related to the applied voltages. It's going to be the space charge regions, the distance is going to be modulated with the applied voltages. Of course, it is obvious that the minority carrier injection is related to the applied voltages. Now, let's compare these two charges. Okay? How can you compare those two charges? Comparison. Space charge and injected minority charge. There's some numbers. Okay. Injected minority carrier case, I just give you the numbers. The VD 0, 0.2, 0.4, 0.6, and the capacitance turned out to be 0.275, 621, 1403. That is femto Faraday. And then QD, the charges 0.0071, that is femtocoulombs, 16 and 36. Oh no. It's all in your notes, so you're gonna have to make a copy of this. 0 and 0.0071 and 16 and 36 picocoulombs now this time. So we can see the dramatic changes in the charges and the capacitance as well. Now, what about the space charge? In the space charge case, VD is equal to 0 here. And above this, we have values minus 0.3, and also minus 0.7 volts. Okay, and then 0.2, 0.4, 0.6. We have values of C junction capacitance, and then the QVD. Here 71 femtofaraday and 82, 95, 0.95. Okay. And 106, 120, 158. And about the coolant, minus 56 femto, minus 26, here the 0, and 20, 43, 71. It's not a dramatically increase. All this are femtocoulombs. So if you compare these two, we can see that if you plot the stored charges with respect to the applied voltages, okay, then the injected minority carrier QF is going to be increased in this fashion with the voltages. But in space charge stored capacitance, the charges, is going to increase in this fashion, okay? Which means at low voltages, this is going to be dominant. Space charge is going to be dominant, but at the high voltages, it just catch up very rapidly, exponentially, so that at high voltages, the injected minority carrier charges will dominate the bipolar functions. It seems obvious, isn't it? It looks obvious because when you look at the space charges, this thing is going to be modulated with the applied voltages, and the injected minority carriers is going to be also modulated with the applied voltages. But this one is much faster, is much sensitive to the applied voltages compared to this. We know how this space charge width is going to be changed with the application of the voltages. That's a square root of that. And this is exponential increase. So you compare that, it is obvious. This result is obvious. So if you if you run the bipolar transistors at low voltages, you have to worry about the space charge thing more than the injected capacitors. Okay, so when you have a hearing aid and a pacemaker, which is working at the low voltages, those bipolar transistors, when you fabricate them, you have to make the stored charges, the junction region, the junction region has to be very carefully fabricated to maintain these charges not that significant. Okay, last time I mentioned that we are not going to have a class on Monday next week. And on Wednesday next week, I'm going to give you the copy of the past finals. Is that the last week? How did you? I forgot the schedule so that I mentioned in the last class.